All right, good morning again, everyone. So today what we're going to do is we are going to look at the enrichment problem that I had posted yesterday. I'm going to share my screen with you guys so that you guys can see the problem presented again. So here are the two problems that I gave you guys yesterday. And the question was, you're given this diagram here, okay? I want you to go through and explain why the relationship between this angle here is half of that of the intercepted arc. Or another way of thinking about it, why is this intercepted arc here double that of the inscribed angle? Okay, so that's the question. We recognize a couple things from this week, and that was, and then just to recap again some of the things that we talked about this week, and that was this idea of we have a circle, okay, and in the circle we have a center and we can have two radius, okay, coming together like this, okay. This angle that's inside here, okay, that meets up in the center, okay, formed by the two radius, we call that something. There was a name for this. Does anyone remember what that was? Starts with the letter C, and it's
central angle.
It's a central angle. This guy right here is the central angle, okay? So this guy here, actually, I'm going to use a different letter. I want to call this like A, B, C, and D, right? So ADB, okay, is the central angle. And we also know this other fact, okay, from this week, is that the central angle and the intercepted arc, okay, so arc AB, the intercepted arc, okay, will equal to the central angle. Remember that? That was from this week, okay? So in other words, okay, if the angle over here we call this theta, what would be the angle over here? Guys?
Yeah.
So again,
theta.
If theta. This is theta, okay, what is the angle? What is the arc that's in pink?
Theta.
It's also theta, okay? So it has a 1-to-1 ratio, okay? What I wanted to go through with you guys with the enrichment problem is to show why are these two, why is the intercepted arc double that of the inscribed angle? All right, so that's the task that we have at hand, okay? So anytime that you're asked to prove anything, okay, Sasha, did you draw anything else in the diagram here?
What? Me?
Did you draw anything? Like, did you like when you were thinking about this problem, okay, did you happen to draw anything else that's not included in the diagram?
Not really. I just see that there's no, I didn't really understand it, so I just.
No problem. Okay. Did anyone draw anything in the diagram here at all? If you didn't, it's okay. All right. So what you have to do anytime that you are asked to prove anything, okay, the vast majority of the time, you will need to draw other things, okay? What would be a good, what would be another line segment that we can possibly draw in this diagram? I need everyone to think about this. And this is the part where math gets to be creative, okay? Creativity, there is no cookie cutter structure, right? It's not like you're following a series of steps. You need to like think and create, okay? That's the very definition of what being creative is. There's no right or wrong way of approaching, okay? I need you to think about, is there a line or maybe other angles or other shapes that I can put inside of this diagram to possibly maybe form other relationships?
An angle bisector?
Okay, how so? If you want to create an angle bisector. You want to create, you want to bisect this angle? Is that what you're saying, what you're suggesting? Yes. Okay, if you do that, you're suggesting to draw a line like so?
Yeah.
Okay, and then from there, what other relationships can you form?
Well, then, I mean, I guess that would be 1/2 theta, and then each of those like two arcs formed would be theta.
So those two angles there, I agree, are 1/2 theta. But then the question is, why?
Oh no, it's a quarter theta.
Actually, this angle here and this angle here will be half of this, right? But why would the arc over here turn out to be double that angle? Right? That's the question here. I'll give you all, okay, and maybe we can work backwards from this, okay? So the suggestion I'm going to give everyone is this. We know that all radius, right, in a given circle, are they going to be the same length or different lengths?
Different.
They're going to be the same length. Say that again, Emmett.
Yeah, same.
They're going to be the same lengths. Okay. So if we know that they will all be the same lengths, that is one piece of fact that we can apply that we know will be consistent, okay? So let's see what we can do. If I were to draw another radius, would it be helpful for me to draw a radius like so?
No.
Why would that not be helpful, Sasha?
Because it's not like involving anything of the problem, like with theta and.
Absolutely. If I draw that radius in there, okay, I have no idea what this angle over here is. I have no idea what this angle over here is, right? The only thing I know is that the radius that I drew is going to be the same as the other radius in the problem, okay? Is there another way that I can draw the radius?
Yeah.
Sasha, what do you think?
You can connect it from that, like, the end
infinite
of
amount.
Well, yeah, you could draw it anywhere, but connecting from the middle to where, like, the left side of that angle. Like,
I totally agree. I totally agree. So look, let's give these things some names, shall we? Right? Let's call this guy here, this point right here, A. This point right there is B. And this point right here, C. In the center, we'll call that D. Okay. All right. So having that, and Sasha is suggesting to connect the point on the left, which is point A here, to the center. I totally agree with that. That would be an excellent choice to begin. Okay. Why is that a good choice? Are there any angles that we recognize right now in this diagram?
180.
Well, we know that we formed a triangle in here, right? And I do agree that a triangle, all the angles add up to 180. You see this right here? This angle that I just highlighted, right? Theta. Is there another angle in this setup right now that we know is also theta?
BAD.
Angle BAD. Michael, do you see that?
Yeah, I see it. Yeah.
Why?
Why
is angle BAD over here also theta?
Because of the co-function identity, the co-function. Yeah.
No, but nice try there.
Because they're isosceles triangles and the two angles of the isosceles triangles are congruent.
Why are they isosceles, Kira?
Because the two sides are radiuses, and all radiuses equal the same length, so they
I
must
love
be
that, Kira. Kira, right? So BD is congruent to AD because we recognize they are radii, right? They are radiuses of the circle, right? So therefore, triangle ABD must be an isosceles triangle. I love that. Okay, so where do we go from here? I'm going to make you guys make the following connection. Okay, I am operating under the assertion that I have no idea. I'm gonna switch over here. Let's just put what we're trying to prove aside for a moment. I'm going to erase this. Okay, and I will also erase this. Because that 2 theta over there is what we're trying to like achieve, right? Let's say we don't know what that is, okay? I want to give this angle over here a name, okay? So I want to call angle ADC here beta. I want to call that beta. So if angle ADC is angle beta, right? Is Keen here?
Yeah, Keen's here.
Keen's here. Oh, hey Ty. Keen, can you
Hello.
tell me what is arc AC?
That's also beta.
That is also beta. That's right. That is what we've learned this week, right? The central angle and the intercepted arc will be the same measure, right? Okay, there is something else. I need you all to recall from physical school, when we were in physical school. I want to highlight this, and I want to ask you all to recall the following fact. The following fact, okay? The fact, I want you to tell me, what is the relationship between these 3 things, okay, that I've highlighted in green?
Fine, you go, Kira. It's fine.
No.
Don't they equal each other?
They actually, well, you need to elaborate though, right? But yeah, Ty, why don't you tell us?
So 2 theta plus beta will equal 180.
2 theta plus beta will equal to 180. That is not true.
No. Well, 1 theta plus beta equals 180.
I would agree that these things will add to 180 if they are on the same line, right?
Wait,
But
Yeah,
beta equal to 90?
So 180 minus beta
I thought that's supposed
plus
to equal
2
to
theta
90.
equals
How did
180 minus beta plus 2
They
theta
equal to 90 because of the co-function identity.
Actually, Kira is on the right track, because what she's saying right now,
Equal
she's
to
recreating a
180
theorem that we had learned in school. Okay. I'll
I remember it was like
I'll remind.
the exterior angle.
That's it. This is the exterior angle theorem that I'm trying to have you guys recall, right? And Kira is verbally recreating that proof. Okay, and I love that. Emmett, do you remember what the exterior angle theorem was?
Maybe it's 2 interior angles are greater than that exterior angle.
No, although it has something to do with that.
I think
Okay.
it's 2 interior angles is equal
Guys.
to the exterior angle.
That's it. Beta, which is the exterior angle, is equal to theta plus theta.
Oh yeah, you're right.
It's-
Yeah, I remember
Okay.
that one. The triangle, yeah. I
Theta
remember
is
that.
equal to 2 theta. Wait a second here. If
Wait,
this
didn't
is
I
the
say that
case-
a while ago?
say that again, sorry?
Wait, I said that they equaled each other a while ago.
They said equal. You weren't specific. That's why I asked you to elaborate.
Yeah. Oh.
Right? It's not that beta and theta are the same, right? It's that beta is equal to the sum of the two angles there. Okay? So wait a minute. By me writing down this last statement here, I've pretty much accomplished the first proof. Do you guys see how or why?
Yeah.
How so, Ty?
But yeah, can you go back to the what's it called? The original statement? Like
The original
the
statement?
given?
Sure.
Yeah, the given.
the statement was this. It was prove that the inscribed angle, which is this guy right here, is equal to half of the intercepted arc, which is this guy right there.
So you could what you can do is just divide both sides by 2, and then you can just get to where you are now.
Yeah, I'll take that. But even more directly, right? What do I have boxed in right here right now?
B equals beta equals 2 theta.
Beta is equal to 2 theta. So wait a minute. If beta is equal to 2 theta, what can I replace that pink arc with?
2 theta.
2 theta.
2 theta.
There we go.
That's it. And we've proven this fact. Okay, so the inscribed angle, okay, is going to be half of that intercepted arc. That's it. This is the proof. Okay? That's the proof right there.
Yeah.
Okay, so why am I asking you to go through this? Because in about a week and a half or so, okay, this is going to be another theorem that you will be using, okay, in your assignments. Salcon will go over something similar, okay, but this is an enrichment problem that I feel like every geometry student should go through and experience, okay. So again, we have the intercepted arc is going to be double that of the inscribed angle. Pretty cool. All right. Yesterday, I gave you guys 2 enrichment problems, right? This was the second one. Okay. All right. So
what we did a while ago is the exterior angle theorem, right? Or something similar to that?
So this theorem, you're asking for a name for this, right?
Yep.
Okay. So this was called, so this guy right here, this is called an inscribed angle theorem.
Oh, okay.
This is an
Is it similar?
inscribed angle theorem. This is the inscribed angle theorem.
Is it similar to the interior angle theorem?
It's not similar to it because, hold on. So this is the inscribed angle theorem. Okay. So again, this is called the inscribed angle theorem. This is not similar to the exterior angle theorem because here in this case we're dealing with 2 chords, right? Technically, we're not dealing with a triangle here. However, all those concepts, okay, related to triangles, they are still applicable. Okay, so what we're talking about again for this inscribed angle theorem is the intercepted arc will be double in measure compared to the inscribed angle. That is the relationship. That is the takeaway. Okay.
Okay.
If anything else you didn't quite get with the proof, okay, this is the main takeaway here. Okay.
Got it.
All right. So we're gonna take a look at this guy right now. Okay, how to prove this. Okay, having gone through the experience that you guys just went through with me, right? What would be good things to draw? What do you guys suggest?
I say we could split.
Sure.
We can draw a I guess the draw down the radius vertically.
Okay. Yeah, I agree. Okay. So from that inscribed angle, draw a radius down to the center, right?
Yeah, from theta.
Say that again. I'm sorry.
From theta down to the radius.
That's right. So I'm gonna go over here.
Yeah.
So Ty is saying, draw a radius like so. Is it guaranteed that this radius that I drew will bisect theta?
No.
Not necessarily. I hope that you guys recognize that, okay? It's not a guarantee, okay, that the radius that was just drawn bisect theta. It's not guaranteed. Okay.
Mr. Chan,
Yeah.
Wait, I have a suggestion for another line to draw.
Okay.
Oh, wait, can you see my screen like a whiteboard, or that you can't?
Can
Can you see it?
you bring your whiteboard closer to the camera?
No, this is like the screen.
This is
I tried
Uh,
to do
No,
it through
it's
the
not,
screen.
it's not a whiteboard. No, there's no whiteboard. There's no whiteboard behind you or anything like that.
No, it was like a thing in Google Classroom. It wasn't working. All right.
screen.
Oh,
Yeah. I was like trying to draw through Google Classroom on them, but it won't work. So from the radius, I think that
You'll
you
need
should
to
draw.
you'll need to share your screen in that case then.
Never mind. It'll be fine. So like from the radius to like where the line meets the circle on both sides, I think we should draw lines.
I agree. So you know what? Let's give these things or actually before we call. You're saying to do this, right?
Yes.
Okay. I totally agree. Okay. So right now, okay, again, just to keep in mind, okay, our end goal is to show that the intercepted arc will be double that of the inscribed angle, okay? Let's just keep that in mind. I am just going to move this over because I don't really, whoops. I'm just going to move that statement over because I don't really need that right now and it's a little intrusive, okay? And I'm going to get rid of this. Okay, and I'm going to get rid of this angle theta right now because, again, it's intrusive. So what I'm going to ask everyone to do, okay, we have two triangles drawn right now, okay? What is special about these two triangles?
we could form SSS.
I like the fact that you're trying to relate the two triangles together, but they do not have to be congruent based on SSS.
They're isosceles?
That's right. Emmett, why are both of these isosceles triangles?
Because they both contain two radii, so they have to.
They both contain radii, right?
Two radii.
So this radii is congruent to this radii, and this radii is congruent to itself, right?
Mm-hmm.
Yeah.
One more time. Is it a guarantee? Is it a guarantee that this angle over here is equal to this angle over here?
No.
It's not a guarantee. Is it a guarantee that this chord is equal to that chord?
Yes.
No.
It's not a guarantee.
No.
Well,
it's not a guarantee.
We need another angle or something to prove.
Right. Okay. So because of this, okay, we cannot say that these two isosceles triangles are congruent based on any of those theorems. We cannot say that these two triangles are congruent based on SAS or SSS or ASA. We can't say that they're congruent, okay? So
wait, Mr. Chan, quick question.
Yeah.
Why are there two dash marks on one of the radii?
I'm sorry, there should be one dash mark.
They have the same length.
Yep. Should be one dash mark. You're right. Okay, so these two triangles are isosceles. That's all we have going for us right now, okay? This is actually the algebraic process. Right now, we don't have much going for us. So whenever we do not have things going for us, okay, the thing to do as scientists and as mathematicians is always to name the things that you don't know. And then from there, maybe perhaps we can work backwards and figure things out, okay? So the thing to do is, okay, if I call this guy right here A, and I call this guy right here B, okay, are there any other angles in this diagram right now that is also angle A and angle B?
Yeah.
Which angles?
The two other angles.
Yeah.
Wait, the arc? No.
Well, yeah, I think
Oh yeah. The opposite of each other.
Yeah.
Like,
That's right.
so
The two other
This
base
angle over
angles.
here is A,
the
isn't
other
it?
base.
yeah, exactly.
And the other one must be B, right? Okay.
Yep.
So now that we have this, okay, what I'm going to do, okay, this is going to blow your minds, okay? Watch this. If I do this, okay, I want to extend that radius over here just a little more, okay? No one suggested this, but I'm gonna throw this out there. Why am I doing this? Why am I extending that radius down like so?
To make it a diameter.
I'm trying to make it a diameter. Look at what we did in the early part of today, right? We figured out, that this angle here, that this angle here and this angle over here have that relationship, right? We just proved it. Can we apply this concept to the diagram that's on the right?
Yes.
Yeah.
Yeah.
We can, can't we, right? So wait a minute. If the angle up top over here I'm calling A, what would be this angle over here?
2A.
Sasha?
A 2A.
It must be 2A. Wait a minute. If I'm calling this angle over here on the right B, what would be the angle of the intercepted arc?
2B.
2B.
It must be 2B. This must be 2B. This must be 2B. Wait a minute. I have something here now, right? Check this out. What is A plus B equal to originally?
Theta.
Ty, you're absolutely right. Did everyone catch that? A plus B is equal to theta?
Yep.
So if A plus B is equal to theta, and wait a minute, now what is this entire arc, this entire thing added together?
2A plus 2B.
2 theta.
2A plus 2B, right? It's 2A plus 2B. And 2A plus 2B, the last I checked, right, there's a common factor. If I factor that out, it's 2 times what? What goes inside the parentheses?
A plus
A
B.
times
Two times
B.
A plus B.
A plus B. What is another way of
Okay.
representing this? It's 2 times theta.
Okay.
So we just proved
What
it.
theorem is this?
Say that again, I'm sorry?
What theorem is this? This is the...
So again, this is the same theorem, okay? One more time, what we just proved, okay, is that the inscribed angle will be half of the intercepted arc. That's what we just proved.
Okay, got it.
Again, the inscribed angle is half of the intercepted arc. That's what we just proved. This is the inscribed
Got
angle
it.
theorem, okay? So one more time. That's the relationship. We just did that in like 5 minutes. Well, maybe 10, okay? So this angle and this angle have that ratio, okay? What we're going to do, and I'm going to post this after office hours today, right? If you notice, okay, that the 2 chords right now that I have drawn, okay, in these two situations, one of the chord, okay, is to the is on one side of the center, right? And then the other chord passes through the center of the circle. The second situation is I have a chord on one side of the center and I have another chord on the other side of the center. Is there another way that I can draw two chords in a circle
Just draw
forming an inscribed
the
angle?
center.
Is there another way?
Infinite amount.
There's actually only 3 different ways that I can draw.
Wait, can't you do it the central angle style? Like the
No.
central angle. We can't
There's
do
a
that.
third way. Can you guys think of a third way that I can draw an inscribed angle?
Mirroring the first one.
Not mirroring the first one, because if I mirror the first one, it's going to be the same thing, just a reflection of it, right? So it's technically the same thing. But is there another
Why
way?
not mirror the second one?
Say that again.
Why not mirror the second one?
I don't want to mirror it, because if I mirror it, okay, it will be pretty much the same kind of setup. I want to draw.
Maybe one that creates a 90-degree angle in the circle. I don't know.
I want to draw 2 chords forming an inscribed angle, okay? And the third possible way would be to draw it like this. Okay? Where, again, the 2 chords, okay, are on one side of the center. Notice, okay? Look at the differences between the way that the 3 diagrams are drawn right now. Look closely here, guys, right? The 2 that we went through together, okay, one chord is on one side of the center, the other chord passes through it. The second situation that we looked at is both chords are on either side of the center. The last possible way that we can draw an inscribed angle is by having both chords be on the same side, right, of one side of the center. And this guy right here, okay, is what I'm going to have you guys think about today, okay, as the third proof, okay? And again, the way in which you go about this, okay, is going to be very, very similar. This last one here is it's slightly more challenging, okay, but the approach is all the same, okay? You will need to draw other lines, okay, and to make other connections, okay, but the idea is very, very similar, and it is still part of, Michael, what's the name of this theorem again?
Inscribed angle theorem.
That's right. It is still all part of the inscribed angle theorem, okay?
But
So the
Mr.
inscribed
Chan,
angle theorem has 3 parts to it, okay? These are the 3 parts, okay?
Mr. Chan,
Yeah, Emma, what's up?
it's still not possible to get an angle greater than 360 here, though, right?
You will never get an angle greater than 360 in a circle, just because 360 is an accepted number that, you know, humans have invented, okay? This is like a standard that we are going by.
Yeah, you can't get further than 360 considering 360 is just all around.
Actually, next week in the Khan Academy assignments, okay, there will be some assignments going through exploring this idea that this concept of 360 is purely man-made, that there's no there's some rhyme reason for why we use 360, because 360 has like a lot of different multiples. Have a lot of different factors, which comes in super handy for, like, you know, problem solving. But other than that, okay, 360 is entirely man-made, okay?
I know.
You know about that, right?
We use
Like
for
the
360
hours,
pioneered
days,
by the
and
Romans?
years.
What was that one at a time?
Wasn't 360 pioneered by the Romans? Like, pretty much anything divisible by 12 was because of the Romans.
Yeah, I figured they were just very obsessed with the number 12.
I mean, 360 is divisible by 12. 12 times 30 is 360.
360 is divisible by a lot of different numbers, and actually it is very convenient to have the number of degrees in a circle be defined as 360 purely because of that fact. But again, that number is man-made. Next week's assignment, okay, as you go through Khan Academy, they're going to explore this idea that we don't need to limit ourselves to this man-made figure, okay? Pi actually is not a man-made number, okay, and it is a number that exists in nature with or without us, okay?
Pi.
Pi exists, yes, pi, 3.14, that irrational number. And you're going to learn about this concept called what a radian measure is. But again, this is going a little above and beyond the scope of the course. But I think it's all really, really worthwhile just to explore a little more. Anyhows, okay? That this right here, okay, is something that's going to be on the regions, but they're not going to ask you to recreate it, okay? You will, at the very least, be expected to know how to apply it, okay? All right, I'm going to stop recording just because that concludes this proof. Again, what I'm going to do today, later on, is I'm going to post this image up, okay, in Google Classroom and ask everyone to repeat the same process again and try to do this. And this time, those who are present, okay, I want you to use the techniques that I've shown you, okay, and really do attempt to try this, because I do believe that all geometry students should go through this process. It's like a rite of passage, in my opinion. Okay. All right. I'm going to stop recording.
Thank you.